Hello everyone, welcome to my presentation. My name is Tao Wang from the University of Sheffield. So this work is finished with the help of our co-authors from the University of Sheffield as well as Siemens Gamesa Renewable Energy. The title is Multivariable Generalized Predictive Speed Control for PMSM with Enhanced Lumberger Speed Observer. So firstly, I will give a brief introduction to the background, and then I will introduce the proposed control strategy, and then I will show some simulation results, and finally, I will give a brief discussion. So firstly, let's have a look at the Generalized Predictive Control, GPC. GPC is actually a special type of MPC. MPC, the Model Predictive Control, is widely used in machine drive and power electronic fields. And in this figure, we can see the main difference among the conventional PI, the FCS MPC, the finite control set, which is very widely used now, and the GPC with long horizon. So the difference is that if you want to drive this car, if you use PI, you are just always looking back because the PI is based on the past error of the control, and the FCS MPC is looking forward, but the prediction horizon is very short, which means that you can only see very short distance ahead. And the GPC, it has long prediction horizon. So the GPC as well as other MPC types, they usually have better dynamic performance and disturbance rejection capability than conventional PI. So the reason is that by predicting future states, a control problem is transformed into an optimization problem, and the control performance can be improved. So here is the comparison between GPC and the widely used FCS MPC. So we will show some good features of GPC. Here is the control structure of FCS MPC. So firstly we build this QP, quadratic programming problem, and then we use this traversing optimization method to solve this QP problem. And the traversing optimization is actually by applying all the candidate voltage vectors to the QP problem, and finally select the best one that minimizes the cost function, so we can directly obtain the voltage vector, so we do not need any PWM modules. And the main difference of GPC from FCS MPC is the solver. So GPC also builds a QP problem, but it solves this problem with some mathematical solvers. So it can directly get the command voltage and uses a PWM to get the switch signals. So here in this table, we can see the differences. For the GPC has longer prediction horizon because it uses a matrix form, compact matrix form to do the prediction and the optimization. But for the FCS MPC, only one step or no more than two steps can be found in the literature. And the switching frequency, the GPC uses PWM, so the switching frequency is fixed, which means that the current quality is better, and also the loss can be reduced. And the static error, so the GPC can inherently avoid all the static error caused by, for example, the parameter mismatches, but the FCS MPC cannot inherently avoid this static error. So as for the computation burden, the GPC, its computation burden will increase in a squared relation with the prediction horizon, but the FCS MPC, its computation burden increases much faster because it's related with the prediction horizon and voltage level number of the converter in an exponential manner. So the GPC has long prediction horizon, so it is especially suitable to control relatively slow dynamics, for example, the speed and the position. So in this paper, we will use GPC to control the speed as well as the current. So in order to use the GPC for the PMSM, we will face two main problems. The first one is the speed measurement noise. The GPC has wide control bandwidth, which is actually a very good feature. But on the contrary, the wide control bandwidth also makes the GPC sensitive to measurement noises. So the measured speed through encoder may have some considerable noises. So usually we have two methods to calculate the speed from the encoder pulses. One is the M method, one is the T method. So usually we use M method in a relatively lower speed range. And so if we use M method, we are just calculating the speed by counting the pulses that can be counted in each sampling period of our controller. So in this figure, we can see that even if the actual speed is fixed, our calculated speed can still have some noises. For example, in some period, sampling period, we will only count 2 times of the pulses, and sometimes we can count 3 times. So according to this pulse number, the calculated speed will also have some noise. So we have the mathematical model of the magnitude of the noise signal and also the frequency of the noise. So here is the simulation result of the actual speed, the red line, and the speed calculated by the encoder, which is the black waveform. We can see noises here. So if we do not take any measures to the noise, if we directly use the GPC to control the speed of a PMSM, we will get this result in this figure. We can see that the speed is actually tracked very well, but we can see the current, it contains very significant distortion, high frequency distortion, which will cause some more loss and some noises and so on. So this is unacceptable actually. So we must take some measures to filter out these noises, but the ordinary low-pass filter LPF cannot be used for the stability concerns because the LPF will cause some phase lag to the feedback loop. And our GPC has a wide control bandwidth, so this phase lag will cause more stability issues than the LPF applied to a PI controlled system. So the GPC and the LPF cannot be combined. We do not need to. We should not use external LPF directly added to the feedback loop. So we alternatively we should use some speed observer, so which can remove the phase lag. And the second problem is that the periodic disturbances that is widely existed in our PMSM drive system, from the back EMF harmonics, the Corrigan torque, the load torque, and the dead time of the converter, and so on. So these periodic disturbances will cause speed ripple. And because we use the speed observer to filter out the noises, so this filter will also filter out at least part of the speed ripple that should have been fed back to the controller. So this information is filtered out by our observer. So the GPC cannot well mitigate the speed ripples in spite of its good disturbance rejection capability, because this feedback signal, the noise as well as part of the disturbance signal are both removed. So our target is to remain the low order speed ripple while filter out the speed measurement noise. So we need to filter out noise, but keep the low order speed ripple information be fed back to the GPC. So let's have a look at the proposed control strategy to solve these two problems. Firstly, the control structure. We have a non-cascaded multivariable GPC, so both the speed and the current are controlled with a single controller. And here we have a PIR based on Nürnberger observer. So for conventional Nürnberger observer, we just use PI to remove the error, the estimation error. But here, in order to keep the low order speed ripple signal, we just add a resident controller adaptive resonant controller, which can change its resonant frequency according to our rotor speed. So with this PIR-based numeric observer, we can remove the noise but keep the low-order speed ripple information. So the long cascaded structure can the coupling between the speed and current is better considered in the prediction. And the PIR-based numeric observer, it filters out the noises without phase lag, but remains low-order speed ripple. And here, let's have a look at the GPC implementation. The GPC is implemented with 3 steps. Firstly, the prediction. So the GPC is based on a multiple step ahead prediction, and the model is based on incremental model rather than the original variables. So here, delta U, delta X, so we use the increment of the variables. And the cost function, so the cost function is a quadratic form, and the penalty is given to the input. And the solution, this is the expression of the solution, and this solution is actually the increment of the input voltage, but we should use some extra integrator or accumulator to get the final input voltage. So this incremental or accumulator is just the reason why GPC can inherently avoid the static error. And here is the current constraint. So for the proposed non-cascaded structure, the current constraint is a tricky issue. For conventional structure with cascaded loops, so we just need to add some limiter to the reference or the output of the outer loop or the reference of the inner loop. So between the two loops, we just need to add some limiters. But for the non-cascaded structure, the variables are hidden inside the controller, so we cannot place some limiters to it. So we proposed an external constraint based on the deadbeat principle. So here is the equation, and here is the flow chart. So generally speaking, if the GPC works well, the current will not exceed the limitation. We will just use the command obtained from the GPC. But if not, if we predict that the solution provided by the GPC will cause some overcurrent, we will just abandon that solution of the GPC. We will replace it with the deadbeat-based current equation calculated in this way. So we have a choice between the deadbeat and the GPC. So this choice will only happen when the current constraint is triggered. So here we will show some simulation results. This is the parameter of the simulation system, and these 3 figures are the results of multivariable GPC without any speed observer. As stated before, the speed measurement noise will cause some current distortion in our experiment results. So here, in the simulation results, we can also see this high frequency distortion in the current. And the noise in the speed can also be observed. So from this result, we can see that the speed measurement noise causes unacceptable current distortion, and the speed observer is necessary. So the second slide, the proposed strategy. Here we apply the multivariable GPC with the speed observer. So as for the speed observer, so before 0.2 seconds, we do not enable the resonant controller in the observer. So we can see that the average speed is tracked very well, but we can see low order speed ripple, mainly 6th order speed ripple can be observed. But after enabling the resonant controller, we can see the speed, the low order ripple is removed. And if we give a wide range speed step, we will see that we can track the reference very well without any overshoot. And the current constraint can be effectively achieved. So the 3 main functions, the multivariable GPC, the PIR-based speed observer, and the current constraint can all be achieved, are all effective. And finally, let's have a comparison with cascaded PIR. So in order to mitigate the low-order speed ripple, we usually use some PIR, PI plus resonant controllers too. So the proposed GPC, we can see the step response is very fast and no overshoot. And the steady state performance is just similar as the PIR. But the step response is much better than PIR. And the node disturbance comparison, we can see that the proposed GPC will have a similar transient peak. Transient peak is just similar as the PIR, but the transient duration of the GPC is slightly larger than the PIR. So we can have the following conclusions. Firstly, the proposed multivariable GPC shows good performance in step response, periodic disturbance mitigation, and noise rejection. But node disturbance rejection capability can be further improved. So it is worse than the cascaded PIR. And alternative solution to noise issues of GPC, we can also enable an internal LPF to the GPC rather than using the external observer. So about this topic, we have published another journal paper. If you are interested in this topic, you can just search this paper. So this is all of my presentation. Thanks for your attention. If you have any questions, I'm very glad to answer you. Thank you very much.